Hello, everybody. We are on to our next big topic, which is the topology of the real numbers. And in this video, we're going to look at a definition of what are called open sets. So open sets are going to be a generalization of the open intervals that we've been using all this time. So for example, you remember we've been talking about L coins. So you might look at an L-centered open interval, and the open, as we defined it, which just meant that you didn't include the endpoints. So we want to somehow generalize this to arbitrary sets where they don't have to be necessarily intervals. So we're going to start here with a definition of what's called an interior point. So if we have an element, let's call it A, in a subset S. All right, and of course we're working here in the real numbers, but this definition actually, generalizes quite a bit. So this element is called an interior point. So an interior point of S if S contains an A coin. So I have some set S, and I don't know exactly what it looks like, but somewhere is this point A, and in order for A to be an interior point, I need to be able to find some A coin that lies completely inside of S. Right? So I can look at any point in S and ask, is it an interior point? And so I can actually build the set of all interior points of S. And let's give some notation for that. We're going to let I of S denote the set of interior points of S. All right, and so now we can define an open set through this I of S set by just saying, well, a set is going to be open if all of its points are interior points. So we call S an open set if I of S is equal to S, right? So if you think of this equality as being two subset inclusions, I of S is a subset of S, that's just clear by definition, right? You're only looking at points in S and asking, are they interior or not? So this direction is clear. It's the other direction, right? That's at issue. Is every point of S an interior point? And if the answer to that question is yes, then S is an open set. So if you go back up to our open intervals and say, well, is this an open set? And you say, well, take any point in the set. Does the interval contain a coin, right, around that point? So if this was my little a, then yeah, all right, I can fit this in. I can always fit a little coin in there. Of course, this is following from our density properties. Okay, so intervals are definitely examples of open sets. All right, we can make that precise. So let's do that as an example. So every open interval is an open set. So the argument, right, is, well, let's say we have an interval A to C, and we choose some point B inside that interval. Okay, so all this is living inside the real numbers. Then, okay, let's draw the picture. So we have A, we have B, or rather C over here, and then somewhere in the middle we have B. Okay, what I can do is I can ask how far away B is from A. So that's this distance here, and that would of course be B minus A. I could also ask how far away is B from C. and that would be C minus B. And now, if I take B minus A and I cut it in half, then I'm going to get a point which is definitely, right, halfway in between. Okay, so I want this distance here to be B minus A over 2. And I could do the same thing on this side. And I can make, let's go halfway. All right. So halfway, I can find some point where the distance now is C minus A over 2. Now, one of these is bigger than the other one, or they could be equal, but I'm going to take the smaller of the two. Okay, so I'm going to set epsilon equal to the smaller of B minus A over 2 and C minus B over 2. And that's the size of the B, or the B coin that I want to write down. All right? So in this picture, you visually can see that it's the B minus A over 2, which is smaller than the C minus A over 2. And so that's what I would actually use. The B minus A over 2 is my epsilon. So then over here, you'd have B minus epsilon and B plus epsilon. Since I'm taking the smaller of the two, I know that this interval is going to completely lie inside of the original interval. So B minus epsilon comma B plus epsilon is contained in the interval A to C. And so we've just found a B coin inside of our interval. And since B was just some arbitrary point in the open interval, we've shown that every point in the interval is an interior point, and hence the whole set is open. Now, one small caveat is it's not really clear what you would do if this was an infinite interval, right? So maybe something of the form negative infinity to C, or A to infinity, or even infinity to infinity. But if you just look at one of these in that case as just saying, well, okay, that's infinity, I'm not going to take that one, right? So for example, if I said, okay, let's go from A to infinity, and then I have a B somewhere, well, there's no point in taking the distance to the right. That's just going to be infinite. So I would just, in this case, take this B minus A over 2, all right? Well, that's B minus A, but I would cut that in half, right? And look at B minus A over 2. I'd use that as the size of my B coin. And if it's infinity to infinity, well, then I can just take any B coin I like, and that's going to certainly lie on the real number line. So every open interval, even ones that go off to infinity, are going to be open sets. Okay, another example, the empty set is an open set. Well, this seems almost counterintuitive. How are you going to put some sort of open interval right, around points that don't exist? But that's actually the point, right? If I ask what are the interior points of the empty set, all right, well, there aren't any, right? There are no points such that there is a coin that is completely contained in the empty set, right? So this is an empty set, right? There are no interior points, but that's exactly the set. Okay, so it's one of these vacuously true statements. All right, another example, right? So we want to get something somewhat new here. Let's say I take the union of two open intervals. So this is going to be an empty set because, well, we already know that each of the intervals themselves is open. And so if I take any point inside either one of these pieces, then I know that there's going to be a coin that lies completely inside that side of the interval. Well, that's all you need, right? It doesn't matter that it doesn't end up in 8, 12 when you choose some point between negative 3 and 4. So this is also an open set. So you can see now for the first time we have some sort of generalization, right? We can start piecing these open intervals together to get bigger open sets. Now, how about a non-example? Let's say I take the half open interval, -3, 4, but I'm closing it off on the right-hand side, so 4 is included. So this is not open. And it's not open because of this 4 being included now, since it does not contain a 4 coin. All right, if I draw the picture here, I have -3, I have 4. Okay, now I have this point 4. If I want to put any coin around it, it's fine. I can go to the left quite a bit, but to the right, I'm leaving, right? I'm leaving the set, and there's no way around that. When 4 wasn't included, I didn't have this problem because I didn't need to put an open interval around 4. All right, I only had to do it around points that were slightly to the left of 4, and I could do that by just making them really tiny. All right. Now, this third example we gave with a union of open intervals, it'd be nice to know if that generalizes all the time, and the answer is it does. So here is actually a theorem, which is that unions of open sets are open. Okay, and there's nothing special about it just being 2 of them. I can actually take any collection. So the union of any collection, even an uncountable collection, does not matter. Any collection of open sets is an open set. Okay, so this is going to be pretty handy. Now, I'm going to give a proof here, and maybe the most important part of the proof is how I'm going to write down any collection of open sets. All right. What students are very often tempted to do to try to prove this is say, okay, well, I'm going to write down a bunch of open sets. Let's call them U1, U2, U3, etc. However, if I do that, right, if I just start by saying, oh, there's my sets, U1, U2, U3, I am already assuming that I have a countable collection, right, that I can count them off. Already assumes the collection is countable. And that's too strong. We don't want to assume that it's a countable collection. We want it to work for any collection. So the way I handle this is by writing down what I'm going to call an indexing set. So it's some way of labeling our sets, right? But it doesn't have to be with positive integers. It could be with real numbers. It could be with something even, bigger than the real numbers. Okay, I don't know. But I'm just going to say let I be an indexing set. So this is some set which is in bijection with all of the open sets I'm trying to take the union of. Okay? So I is some indexing set, and we let, all right, now my sets, I'm going to call them S sub alpha, and alpha is going to run through I. Okay, so this is going to be a collection of open sets. So each one of these S alpha is an open set. All right, and how many are there? Well, there's one for each element in this indexing set I. All right. Now, if I want to show that the union is an open set, then I need to show that every element of the union is an interior point. Now, what is the union? The union just consists of all the points that are in any of these S alphas. Okay? So if I have some point, though, then it lies in at least one of these S alphas. So let me start with one. So if I have some point which is in one of the S alphas, well, because S alpha itself is an open set, then I know that S alpha contains an A coin. Right? So let's say A minus epsilon, A plus epsilon, right? For some epsilon positive. Okay, but from there, what do we know? Well, this interval a minus epsilon, a plus epsilon is contained in S alpha. That's what it means, that S alpha contains the A coin. However, every one of these S alphas is contained in the union, right? Over all, well, maybe I won't use alpha down here. How about I'll call it like I and I, S sub I. And so what we've just shown is that the union contains an A coin. And A was just some arbitrary element in one of these S alphas, and those S alphas are what make up the union. So thus, the union is open. Okay, so in other words over here, right, what are we saying? A is an interior point of the union. And again, since we chose A arbitrarily, every point then is an interior point. Okay, so that's the proof. It's actually pretty straightforward. The important point here actually is really this bit about indexing sets. All right, well, if we know that unions of open sets are open, then that begs the question, well, what about intersections? And it turns out that we have to be a little more careful with intersections. So we'll get a theorem, but it's not as nice as we like. The theorem is that finite intersections of open sets are open. All right, now compare this, right, with unions. It was any collection of open sets. If we took the union, it was still open. This is a much more severe restriction. Now, this is not to say that if you have an infinite collection of open sets and you take their intersection, that it's necessarily not open. But if you want to guarantee openness, you can only take finite intersections. All right, so the statement is the intersection of any finite collection of open sets is open. Okay, and yeah, we'll prove this as well. So now, unlike before where I had to take any collection, here I can take a finite collection, so I can number them in a nice, obvious way. So I'll let S1 through Sn, all right, I'll put some brackets here, be a collection of open sets. All right, I want to show that the intersection of all of these sets is open. So I need to choose some element from the intersection and show that it's an interior point. So I'll take some A in the intersection. So we'll say we'll go from k equals 1 to n, s sub k. Then, well, what do I know? I know that this A is an element of each of these SKs. And each of these SKs is an open set. So that means that each of these SKs contains an A coin. So there exist A coins, not just one, but plural. And let's label them like A minus epsilon 1, A plus epsilon 1. So that'll be the coin that's in S1. All right, and there's going to be one for each of these open sets. So I'll have an A minus epsilon n, A plus epsilon n, such that we have that A minus epsilon k, A plus epsilon k, is contained in S sub k. All right, and this is for I, or k equals 1 to n. Okay, so because A is in the intersection, it's in each SK, and because each SK is open, each of these SKs has to contain an A coin. Okay, and these are the A coins that we're writing down. Now, amongst all of these A coins, at least one of them has the smallest radius. Okay, so let's define epsilon, no subscript, to be the smallest radius. Okay, so it's the smallest of all these epsilons. Okay, so from this, what do we know? Well, if I took the A coin with radius epsilon, that has a smaller radius than any of these, right? Or at least less than or equal to any of these. So this will be contained in all of these. Right? So pictorially, right, you're just saying, oh, I have some A, and maybe here's some A minus epsilon k and A minus epsilon or plus epsilon k. And if I take some smaller radius, then it's going to live inside, right? So there'd be A minus epsilon, A plus epsilon. So it'll be some subset. Okay, but I also know that this is contained in Sk, right? That was how we defined this A coin. And this shows me now that this new interval, this new A coin of radius epsilon, is contained in Sk, and this is again for k equals 1 to n. But if it's in each of the Sk's, then it's in their intersection. So this implies that A minus epsilon, A plus epsilon is contained in the intersection of all the Sk's. Okay, so this implies that A is an interior point of the intersection. But that's what we needed to show. We needed to show that every point is an interior point, and we just took an arbitrary point and showed it was an interior point. Okay, so thus the intersection of the SKs is open. All right, now that finishes the proof, but let's just make a little comment. Why did this proof not work for any collection of intersections, right? Or any of open sets? So the point where we made an actual comment about us needing a finite was in this line right here. We said we defined epsilon to be the minimum of all of these radii for all the different A coins we'd written down. And there is no guarantee that an infinite set has a minimal element, right? Imagine if you had an infinite collection and the epsilons you got were precisely, say, points between 1 and 2, right? But not including 1 and 2. This set has no minimal element. So we would not be able to employ the argument after that. So the finite was really necessary in this point. All right, well, that's all we're going to say about open sets for now. In our next video, we'll talk about closed sets.